Okay, thank you. I'm Brian Koch. I'm the VP of Engineering at Quintessent, and today I'm going to talk about our technology for scalable and reliable optical compute interconnects. So there's been a lot of discussion about these. I'm not going to dwell on it, but just to be clear, we're talking about AI ML, XPU to XPU, and memory disaggregation applications. And the requirements for these, without putting numbers in here, because that's set by the customer, it's very clear, though, versus Ethernet, this needs to be much higher bandwidth per fiber, higher bandwidth density, lower latency, more energy efficient. And another one that I'm going to add to that is higher reliability. And I want to take a minute to talk about that. So if you look at, this is a chart showing the failure probability for a 512 channel system after 7 years. And a typical customer requirement could be in the range of 0.1 to 1% failure. And what this is showing is that with typical fits for individual lasers from quantum well technology today, this is not even close to meeting requirements. So typical today is 20 to 200 maybe, and we're realizing that we need to target below 1, we think, for these kinds of applications to be scalable. So I'm going to show you why we think that's possible. And these are the kind of techniques that we're using to do things a little differently than traditional approaches. I'm going to talk about these in the next slides. So the key point that I want to drive home on this slide is that we're developing a very flexible capability. And we can go very high bandwidth per fiber, very high bandwidth density, and do that with low power. So, for example, we're looking at 8 to 32 wavelengths, 25 to 128 gig, and a bandwidth per fiber of up to 4.1 terabits per second. And this is an example of how you might do that. And these are kind of building blocks here. Some of the other speakers have talked about this. We're using a multi-wavelength comb laser made from quantum dots, integrated onto silicon photonics, each laser emitting 8 wavelengths into 8 ring modulators. Excuse me, back. And then we have different lasers centered in different CWDM bands, so we can actually scale this out and then mux them together into a single fiber using a CWDM mux. And this, although this looks like kind of a big chip, it's actually not. It's around 1 millimeter of edge bandwidth density. So you can imagine you can get a lot of bandwidth from a single chip by scaling this out. So this approach combines the advantages of DWDM. So why is DWDM needed? So we want to go wide and parallel to avoid high-speed electrical signal loss and muxing to reduce power and latency. But we also want to combine that with the advantages of high bandwidth density and fewer fibers. So that's the reason for using WDM instead of spatial, parallel spatial. And then there is a limit, though, to how many rings you can put in a row. Each ring has a finite FSR, and eventually they'll start to overlap. So the way we're proposing to get around that is to do CWDM. And CWDM is nice because there's minimal control. These wavelengths can drift within the band, and they don't need to be controlled relative to each other. So that's also efficient. And so, as I mentioned, these are very compact devices, which can save on cost and keep the density high. Another thing that we want to highlight is that we're using quantum dots, and there's several reasons for this, one of them being better temperature performance. And as an example of this, you can see an Li curve here, output power of a laser and wall plug efficiency, and fairly similar at 20 degrees and 80 degrees Celsius. So over 100 milliwatts output power in both cases, and over 25% wall plug efficiency. This is a demonstrated device. The quantum dots also offer reduced reflection sensitivity, which can avoid the use of isolators. And when you're doing an integrated device, that's particularly important because it's very hard to put isolators onto a chip. So we think this is pretty important. We've also shown that these can have very low noise gain. So we've demonstrated 4 dB noise figure from our SOAs while simultaneously hitting 20% wall plug efficiency. And a lot of people think that quantum dots might have questionable reliability, but what's actually been shown, and I don't have a lot of references in here, but we will in the white paper, there's a lot of research to show that that's actually not the case, and in fact, they're more reliable than quantum well lasers. 2 reasons for this are that the minority carriers are trapped and isolated from surrounding defects, but also the dots actually harden the crystal lattice, inhibiting the defect growth in the first place. So we have some preliminary reliability. This is just 2,000 hours. We kind of just started. But we're aging this at 80 degrees and at 2.5 times the operating current density. So that's up to 10 kiloamps per centimeter squared. Just showing, obviously no disasters here. It looks pretty good, very minimal change. And this is going to continue. We'll keep aging this, but these initial results look promising, and we're pretty confident that we're going to show very, very good reliability from these lasers. Another thing that's interesting about our approach is integrating the laser, which we also believe will improve the reliability. One reason is, compared to a discrete laser, one reason is that there are no facets, which is a common source of defects in lasers. So we completely avoid that. The lasers are completely hermetically sealed. And we have excellent process control because we're doing this at a silicon foundry. So that's another nice advantage. The integrated laser avoids a lot of link loss. So if you have an external laser, you can expect to have a couple dB, maybe 1 dB coupling loss to the fiber, and then again back into the modulator, silicon photonics. So you're right off the bat probably losing about half the light power. And when you're trying to close a link, that's a lot of energy. And by integrating the laser, we can get down to 0.3 dB of coupling loss. So you save a lot of power and energy there. It also avoids a lot of packaging. You don't need another package for the laser. It's right there. And you don't need fibers, which saves cost and saves on edge bandwidth density because you don't need fibers for the light to come in. And it also, having integrated gain, enables new architectures or PICs that were not previously possible, not just from the lasers, but also you can add gain from the amplifiers. If you want to have a longer link or maybe a link with a switch somewhere in the link that adds loss, you can overcome that with an SOA. And those are low noise SOAs, as I mentioned. And so we've shown so far 200 millimeter silicon wafers with quantum dot lasers heterogeneously integrated at Tower onto their PH18MA silicon photonics platform. So it has all the same standard PH18MA devices, including modulators, photodetectors, passives, et cetera, and we're just adding our quantum dot lasers onto that. So the initial lasers, it's still in development, but we're seeing around 10 milliwatts emitted into the 220 nanometer thick waveguides at room temperature, and we've shown operation up to 100 degrees. And these results are absolutely going to improve with ongoing development. And I want to talk a little about the comb laser advantages as well. So we think that this is essential to DWDM approaches. This allows you to use far less lasers than you would otherwise. So in this case, we're getting 32 wavelengths from 4 lasers instead of 32. You can imagine the amount of space that is saved there. These lasers are they're not 8 times bigger than a regular laser. They're around the same size. So can fit a lot more onto the the area. It also reduces the cost because of that. And one other big advantage of the comb laser is that the wavelengths are inherently aligned. You don't need to carefully control the wavelength of each individual laser. They're just locked in phase, and they move together, and the rings can track them together. So that, I think, is also a really big advantage that people, I think, who are trying to do DFB arrays are realizing it's hard, especially if you're trying to do densities like 200 gigahertz spacing or 100 for sure. Whereas for this approach, it's not a problem at all. So these are some of the results we've gotten from some of our comb lasers. So we've shown 25 gigahertz spacing, 50 gigahertz spacing, lots of lines there. But our focus is now mostly on 100 and then also moving to 200 gigahertz spacing. And I think the key thing to note here is that when we say we want to use multi-wavelength comb lasers, a lot of people get concerned about, can you really get enough power out of it per wavelength? And what about the RIN? Isn't there a lot of mode partition noise? And what we've shown now is that no, that those concerns are not really valid anymore. So we've shown lasers with 8 lines, each within 3 dB of power, and each line, the lowest one, about 8 dBm of output power. And the RIN of the worst line is minus 147 dBc per hertz. So this is suitable for even PAM4. And this is all with a wall plug efficiency of around over 25%, actually, of the usable wavelength power compared to the power that was put into the laser. And so I'll end with going back to our vision. So what can you do with this? As I said, it's very flexible. We're not saying we want to do necessarily one thing or another. We want to have this be applicable to whatever a customer wants. But 2 examples are shown here, which are both PCIe Gen 7. And what we could do is we could take half of this PIC that's shown here and just do 16 wavelengths instead of 32 and modulate each wavelength at 128 gig for a 2T link. Alternatively, we could take the 16x 128 gig PAM4 signals, demux them down electrically to 64 gig NRZ, and do 32 wavelengths in the optical domain using this PIC shown here. And some advantages there could be like latency, for example, or just lower power, because NRZ is lower power than PAM4 optically. And this is a BER simulation, and the point I wanted to make is that these simulations are with very low laser powers, so ranging from 0.1 to 0.26 picojoules per bit for 28 gig up to 128 gig PAM4. And that's it. Thank you.
We have time for one question.
I have a question. In those diagrams, where are the SOAs, and are the SOAs also quantum dot materials?
Yeah.
And the other one is about how did you improve the RIN? Was it the mode partition noise you made go away? If so, how? Or do you have comment on that?
Yeah, I do. So there are no SOAs in this architecture. We can add them in, and it uses the exact same material as the laser. So it's the quantum dot gain material, same material, just used as an SOA. And in terms of the RIN, yeah, the key is the quantum dot material. You cannot do this with quantum well lasers, at least to my knowledge. And honestly, I was skeptical at first because I've never seen a multi-wavelength laser with RIN anywhere close to this. But it's really all about the material, and it works. So, you know, I can explain why the quantum dots do that. It's a little bit more involved. So.
Thank you.
Okay, thanks a lot.